for the introduction and inviting me here. So I'll talk about Helly number tandem laws and related problems, hopefully. And this is a joint work with Alon and Sudakov, my advisor. So so let's start with the famous Helly's theorem. So the Helly's theorem states that let's say K1 and Kn are convex sets of R to the power D, such that any D plus one of them intersect. Then all of them intersect. So this is the well-known Helly's theorem. And in general, one can, it's worth mentioning that this D plus one here, it's tight. Why? Because we can, for example, take take n arbitrary hyperplanes in general position, then every D plus one of them, every D of them will have a non-empty intersection, but you cannot guarantee anything that all of them will intersect or not. And in general, one can ask the same question if instead of saying these sets are convex in R to the D, but instead we specify what sets are considered to be convex. And in this case, what we do is that we specify a set. Is this feasible or? Okay. So let's say this F is just a set family. And in this example, F is simply the set of all the convex sets in R to the power D. So these are the convex sets we think of. And in general, the question is something like, what is the minimum H? We want to have some similar statement compared to this one. So what is the minimum H? H, you should think of this D here, so that whenever you have sets K1 up to Kn, actually whenever you have n, whenever you have K1 up to Kn, these are subsets in this, these are sets in this set family, so that any H of them intersect. Then you want to say that all of them intersect. So this is really the same thing as this Helly theorem for convex sets in R to the D, but instead of convex sets, we think of, we look at a general family, set family here. And we can also ask the same question to determine the threshold here for a general set family. Let me give some examples. By the way, if anything is not clear, please ask me about it. Here, or should I?
Here, convex set family mean abstract convexity or just any set family?
You can also impose some conditions, but let me just put it like this now. You can also add some conditions like the intersection is closed undertaking intersection, but yeah. And let me try to give some examples. The first one, let's say F is all the subtrees of a fixed tree T. T is a fixed tree in the beginning, and let's think of F to be all the subtrees. And it's not hard to show that the Helly number, by the way, this H is called the Helly number of this set family, because it's really the Helly statement. And so it's not hard to show actually graph theory exercise that the Helly number is 2. And the second example is this famous convex lattice set. So you take F to be all these things. So K is any convex set in R to the power D. And then you take the intersection, take all the integral points. This is all the integral points inside K. So this is another set family. And then a well-known result is is that the Helly number is 2 to the D, which is way bigger than the Helly number of this convex case. And this is shown by Doignon. Another example is a generalization of Helly's theorem there. So F here is a set family, any set family of subsets in R to the D with the following condition, that for any subfamily of F, the intersection of everything inside this subfamily is a union of at most K convex sets, normal convex sets. So this is a bit long, but if you think of, for example, when you take F to be the set of all the convex sets there, this satisfies the condition with K equal to 1, because however convex sets you take, the intersection is always convex. So it's just a union of one convex set. And then it's shown that in this case, the Helly number is at most a constant, which is dependent on K and D, these two parameters. This was shown by Alon, and later by Matoshek. So these are 3 examples of the Helly numbers of concrete set families. And now let me introduce our setting. So in our setting, we want to think of the Helly number in some very discrete setting. So what do I mean is that let's look at in general a set family. In general, the objects. So here every point is just a point in R to the D, and here every point is inside the universe. The universe is some set X to the power n. N is a parameter, and X is just any set. One should think of 2 special cases. First is X equal to 0, 1, so it's a binary set of binary strings, or X is equal to R. So this means you basically don't care about whatever you choose to be the alphabet. You just choose anything. Actually, our result works for any X, but just for a concrete example, we can think of X to be R. And then all the objects are just vectors or strings inside the space. And then it's one well-known distance is the Hamming distance. We can, for A and B, in this universe, the Hamming distance is simply the number of K, the number of indices, such that the kth bit of the first vector is different from the kth bit of the second vector. Right? And then we can also define the Hamming ball. This is the Hamming distance, and Hamming ball centered at a point P of radius T is denoted by we call it BPT, is the set of all the Q that is in the family, that is in the universe, such that the distance between P and Q is at most T. So this is the normal definition of Hamming-Balls, right? And we are interested in the family of all the Hamming-Balls of the fixed radius. So the family is all the Hamming-Balls in the space x to the power n of radius exactly t. So this is what we want to think about. And the question is, what is the Helly number? Is it clear what the question is?
Yes.
Okay. So I want to mention that this question doesn't come from nowhere, actually, because you might feel this is just a very artificial question. But indeed, when it was a question asked by 3 machine learning people when x is the special case of 0, 1 to the power n. I think in recent years there has been quite some results in machine learning theory to use some certain Helly number to classify the learnability of some learning classes. And this is one of the examples. Although it's a toy example, it's still some connection. Yeah. And so this is a question. The first step to do is to try to guess the answer by maybe some constructions, right? So the construction is quite simple. Let me just describe it here. It actually already occurs in the machine learning paper. So the construction is, for example, just for simplicity, let's think of n to be equal to t plus 1. Because whenever n is at most t, there's nothing to do here. Every Hamming-Ball is just everything. So let's think of the first non-trivial case when n is equal to t plus 1. So here, we can consider all the Hamming-Balls of radius t and centered at p, where p lies in this binary cube. Yeah. So remember that I assume x is either 0, 1 or r, so we can always put p to be 0 or 1, right? So there are 2 to the p of them, 2 to the t plus 1 number of them. We just need to show that these things doesn't intersect while deleting any one of them will intersect. Then the Helly number should be at least this number minus 1. Should be at least this number, actually. So the crucial observation is that every such Hamming-Ball intersects with the 0, 1 cube is really everything minus one specific point, which I call p bar. What is this point? This is just the point when you flip all the bits. So p bar I is equal to 1 minus pi for all I that lies in n. Because then all the bits are different. And all other points in this cube, they are at least the same for one bit, so the distance is at most t. And this is the first observation. So this shows that actually every 2 to the t plus 1 minus 1 of them, of these balls, intersect. The reason is simply if you have one more ball, you will kill one point. And the whole space has 2 to the t plus 1 number of points. you can do this until you kill all of them. And it's not hard to see that also all of them do not intersect. This we can just check by hand. Basically because if you look at the 0, 1 cube, every point will kill the opposite point, and everything is killed. Yeah, so this is the construction. And in general, we can also do the same thing, exactly the same proof, just by looking at t+1 bits to get the same the same bound on the lower bound of the Helly number. So this in general shows that the Helly number of this family is at least 2 to the t+1. Any questions so far? Okay. I should have put some like a t and n here as a subscript of f, but I think it's clear to all of us. Yeah, so for the rest of the talk, I will probably focus more on how to prove the upper bound of this. So our main result is actually this is tight. Yeah, and the proof is like a linear algebra proof, so I think the proof is short and interesting. I'll hopefully give a whole sketch of all the steps. And yeah, so this is what our main result. And in order to do this, we will reduce the problem to all about something like a set pairing equality, which I'll show now.
The upper bound holds for independent of the size of the alphabet?
Yeah, the crucial part is this is really only dependent on t, whenever n is bigger than t+1. Yeah, and actually I'll show two proofs. One is a probabilistic proof, one is an algebraic proof. And the probabilistic proof works already for the binary case. It's really like a 1 page or half a page proof. And the algebraic proof is a bit longer, but that works for the general case. Yeah. So let me first give a reduction step from this thing, the upper bound of this guy, to something that we might look more familiar to us. So what does it mean? So we want to show an upper bound of that guy, of the Helly number. And in other words, we want to know why can the Helly number be big? That's the other way to say the upper bound, right? So for example, let's suppose that the Helly number is bigger than some number h. So this means that h minus 1 is not a Helly number. And in particular, this means that there exist balls b1 up to bn for some n, such that every h minus 1 of them intersect, but all of them do not. Right? Because otherwise, if you cannot find this, then h minus 1 would have been the Helly number of this problem.
So in here, our host subfamily F is supposed to be a finite or countable, because you choose n as a finite n. But if we allow F as an infinite class of the subfamily, then
I think like with some work you can show that also works. But you can assume, for example, you can assume this x to be, for example, integral all the integers as well, because the problem is really a discrete problem. Like with some work you can just show that the alphabet really doesn't change anything as long as it's finite, infinite. Yeah, and yeah. So this is what one. This is the implication of this thing. And indeed, we can now take among all such all such ball families, we can take the family to be minimal, in the sense that you cannot delete any one of them to maintain this property. Right? And then what is happening is that we know that in this, among these n Hamming balls, all of them do not intersect. And also deleting one of them, and also every h minus one of them intersect. So this implies after deleting one ball, all of them cannot intersect all of them will intersect, because otherwise you can just delete that one ball. So this shows that so indeed these and these together, they show that every sorry, I should have wrote b1 up to bm. Maybe that's what you meant. Yeah, because this m might be different from the length of the coordinate. Sorry. So every m minus one of them intersect, but all of them do not intersect. So this is now a very nice property, because then for each
Should it be n minus 1 or h minus 1?
m minus 1. So here it is h minus 1. This is what we already know. Like this is the guarantee of this condition. And then if we take
m is equal to h or something like that.
I'm not sure if you can easily see m is equal to h or not. Like I think yes, but I don't know how to just say it. Like I don't know how to
But if
justify
m
it.
was greater than h, then you have now an example that shows that the Helly number is greater than. I mean, this is an example showing a lower bound of m
Yes.
on the Helly number, no?
Not necessarily.
Why? Because
Because
here you have a family of m sets, every m minus 1 intersect, but the intersection of all of them is empty.
yes.
So that's an example that shows that the Helly number is at least or greater than n, no?
Yes, exactly. Okay, yeah. Then I need to also take this h to be exactly the Helly number. Yes,
Okay,
exactly.
okay.
Yeah, yes, you're right. So, yeah. So, as you said, if we assume the Helly number is h, then there should exist something like this happening. And then this will imply
Okay.
this every m minus 1 of them will intersect, then you can see that indeed this m must be h, right? As Andres pointed out. So in particular, this means that for each I that among this m or h, whatever, there exists a point, let's say a point which is called ai, that lies in all the balls that is not I, because this is non-empty. And also, we can also take bi to be the center of capital Bi, the ball Bi, right? This is just the obvious choice for a point. And then what is happening is the distance, the Hamming distance of ai and bi must be at least t plus 1, because little ai cannot be in capital Bi. Otherwise, all of the stuff will intersect. Like, ai is already in almost everything but Bi, capital Bi. So it cannot be in capital Bi. However, if you look at any bj, compared any ai and bj, then we know that ai is in the ball of capital Bj. Therefore, distance of ai, small ai and small bj should be at most t. This works for any I distinct from j. So this reduction step reduces the problem into something like a set pairing equality. It's not really a set, but like a pairing equality. This is really what we proved. Any questions so far?
So in this case, we apply the theoretic version of the step-family inequality.
Sorry?
In this case, you apply the theoretic version of the step-family.
No, we give another proof. We tried to apply purity, but it didn't work out. If
What-
you apply,
But the statement is very looks like the
Yeah, yeah,
theoretic
yeah.
version.
I think
why
theor-
it does not apply.
the purity will.
What is Ferretti's version of set pair?
Almost exactly that.
So purity, I
What
think.
is the metric?
No, purity is a set system, I think, right?
Okay.
So purity is that you have sets AIs and BIs,
Okay.
so that AI intersect BI is larger than, for example, T, and sets AI intersect BJ is smaller than T. These two properties, plus AI has size A, BI has size B. I think this is purity.
Yeah.
I think this is the purity you meant.
But this is vector, and vector is basically the same as the.
It depends which version. If it's binary, yes. If it's non-binary, I really don't know what to do.
I see.
So indeed, if you apply purity, you can get a not. It's not easy to get an upper bound here.
So basically, you are not applying purity, but applying the proof of purity, right?
It's not. It's
Oh,
also
okay.
not a proof of purity. Like it's harder than. I think it's longer than the proof of purity, and as you will see later, because the problem here is that like for example, if it's a binary string, you can take all the ones to be the entries you're interested in, like to be the set system, and then you can apply purity somehow. This will give you some upper bound, some not very tight upper bound. This will give you something. And in general case, for general alphabet, you can still apply purity in another space, where for each bit, you put an entry of a pair, which is like which bit is it, and also which alphabet or which letter you choose in this bit, and you can apply purity to get a bound, something like a combination number. And you cannot. I don't know how to really connect this. The answer here is. I think it's a plus b minus 2t, choose a minus t. I don't know how to connect these kind of answers to the 2 to the power t plus 1, really. Yeah. Yeah, so it would be very nice if one can just apply purity or something like that. And yeah, that's actually our motivation to find the proof. So the thing we really proved is this. So let A1 up to AM, B1 up to BM be points in the space with the following condition. This is like between AI and BI, the same coordinate. Then the distance is at least t plus 1 between AI and BJ, the distinct coordinate. Then the distance is at most t. And the conclusion is that m is smaller than or equal to 2 to the t plus 1. This is what we really proved. And yes, so there are several things that so now I will give two proofs. The sketch of two proofs. One is probabilistic, as I promised. One is algebraic proof of the whole version when x is everything. And in particular, there's one case. Oh, I will make one further assumption, which is that here it's at least t plus 1, but instead we always assume this is exactly the same as t plus 1. Because one extra trick is required to really handle the case where the distance is larger. If you just do it naively, the kind of bound you will get is that the summation of 2 to the minus distance is at most 1. But then you will not get the right answer here, because if the distance is larger, the weaker the bound you will get. Yeah. So let me first sketch the probabilistic proof. So and also the probabilistic proof works and only works when x is binary. Because indeed, Yeah, there are some reasons. I will explain later. Yeah, so the probabilistic proof is it happens, for example, in the set pair inequality case.
So are you working in the green setting or in the white setting?
I'm working in the green setting.
Green setting.
Green setting is stronger.
Ah,
Like, I'm always working with a case where this is equal to t plus 1, and this is at most to t. Is it clear, or? Because you can check later, like the final bound you will get by whatever I was saying is 2 to the minus distance. AI and BI is at most 1. And you need some extra trick to add something here to make the bound, to make it to let it be that the larger the distance is, the larger this bound is. But now it's not the case. There is an extra thing to apply. For this, you can check our paper for extra stuff. Yes, so this is the simpler case. And then what we do is to try to follow the proof of set pair inequality. So we want to have a bound like this. This means we probably need to define a lot of events so that all the events are disjoint, and also every event happens with exactly this probability, the reciprocal of this probability. And then it's done. So how does this t plus 1 come from? Well, you take something where you have one half to the power distance. That's how you get it. So it's actually quite straightforward. What you do is to sample, for example, alpha, uniformly, sample a binary string alpha uniformly. Right? And then the event is simply like this. Event I is that alpha coincides with the string AI on the subset Si that is defined to be the coordinates k such that AI and BI are different. So this is a set defined by every pair of AI and BI. And this is the set of indices where they are different. And we know every such set has size exactly t plus 1. So actually the most straightforward thing to do is to say that what if alpha coincides with AI on everything of this Si, right? And actually one can check with this condition all these events. So first, clearly the probability is exactly 2 to the minus, which is 2 to the minus t plus 1. This is the probability. And with some work, I will not show here, one can see that every EI and EJ are disjoint with these two conditions. You can just do kind of a case analysis on which bit is the same as AI, which bit is the same as BI, which is the same as BJ. Like, there are not many categories of for each bit there are only finite number of categories. You just need to carefully think about all the cases, and it's easy. So this shows that probability that there exists some epsilon, there exists some EI to happen is equal to the probability that one of them is equal to the summation of the probability that they happen, because they are disjoint. By disjoint, I mean they cannot happen together. And therefore this is at most 1. However, this is also at least m times 2 to the minus t plus 1. So this shows the desired bound. Right. This is really like exercise proof of probabilistic method, right? So this is not that yeah, this is not the most interesting part of the proof. So there are two important information that I want to convey. First is, this is short. Second is, this only works for binary for a particular reason, that this proof only needs two information.
Provided a nice exercise for home, who is going to teach something like this.
Yeah, actually I already put it in the exercises of our algebraic method in combinatorics course. Or probability, both. So indeed, since usually the probabilistic proof, for the probabilistic proofs, you want to prove two events are disjoint. And you cannot see a difference between EI, EJ or EJ, EI. It's not directed, it's really an undirected pair. So indeed, usually we use the information of AI, BJ and AJ, BI together. So, and indeed in this proof, we only need to use that the summation of distance AI, BJ and distance AJ, BI is at most 2t. This is really what we use, plus that the distance f is at least t plus 1. But this is not good enough for other alphabet, because we have an example when alphabet is, for example, 0, 1, 2, then there exists such AIs and BIs so that m is equal to 3 to the power t. So you cannot hope to give a proof that uses this information, yet giving this answer. And you can also show that in this case, if it's the alphabet is 3, then the answer is at most 2. The answer is at most 3 to the t plus 1. So this kind of shows the limit, I think, the limit of a straightforward application of probabilistic method, unless one knows how to differentiate between the two distances. Yeah. Any questions so far? Otherwise, I'll move on to the algebraic proof.
Yeah, always just talk about the.
Oh!
It was better before.
Oh.
It escaped.
I'm sorry about that. Yep. That's why it couldn't go up. Okay, so the second proof is an algebraic proof, which is actually, we think the most interesting part of our paper. So, yeah, so we didn't write it this way, but I want to present it in something that in the way that we came up with the proof. So yeah, and the way to do it is to kind of compare, try to say the probabilistic proof in the way of an algebraic proof, kind of. And the way to do it is, so the first question is like this. So usually, how does an algebraic proof work? So you want to construct a lot of objects and show these objects are linearly independent, and well, the number of objects is at most the rank of the space. But there is an obvious problem here. The rank of the space must be dependent on n. Because, I don't know how, like if there would be a way to directly focus on some fixed number of bits of this space, it would be very nice, but we don't know how to do this. And on the other hand, the other way is to construct something other than let's say a single object, but instead we construct a lot of objects to one index I, for example. So the way I was thinking about is like this. So remember that a notation Si is equal to the set of indices in N, so that AI is the same as Bi. Oh no, where did I go? This is Di. Because S stands for the same, and P stands for different. Sorry. And B is the complement. Yeah. So for each I, I want to construct a set of objects, which I want to represent it as a subspace. So let's define. So before this, I want to say that. Yes. Let's think of now the universe is really all the multilinear polynomials in Rx1 up to xn. Yeah. So then the dimension of this space, is then 2 to the n by nature. So here, this is where the exponential function come into play. And then for each I, I define ui to be the set of polynomials of this form. So this is a product of k that lies in the different part. In the different part, you always take a fixed function, xk minus bik. And then in the same part, you multiply something that can have a freedom. So weird notation, but what I meant is that for each I want to construct a subspace of the set of all the multilinear polynomials, in the sense that in the place where AI and BI are the same, I don't have a choice. In the place which is given by this xk minus bik, you never change it, you never choose this. And in the place where k is in di, where AI, which means AI and BI are different, in the place where they are different, you don't have to choose a choice. In the place where they are the same, where AI is equal to BI, you can take here to be any linear function you want to take, plug with xk plugged inside. So you can take it to be so basically two choices, either a constant or a linear function. So this subspace obviously has dimension 2 to the si. Because is it visible?
Yes.
Because for every k in si, you can choose either you want to plug inside a constant function or a linear function. So the dimension is this guy, which is 2 to the n minus t plus 1. And it will be good enough if we can show that somehow all the UIs, they are independent in the way that you cannot pick anything inside that sum up to 0, because each UI is really a linear subspace. It is. So this is the way we thought of, but we didn't write this way in the paper. And so the way to prove, so the goal the goal is to show that the dimension of is this the notation for you take sum of two linear subspaces and take the span? Okay. So the goal is to show that this is equal to m times is equal to the summation of the dimension of each ui. And then this is enough because this means that on the left hand side this is at most 2 to the n. However, on the right hand side this is at least m times 2 to the n minus t plus 1. So this will follow. The thing will follow. Yes, and the way to do this is by showing that indeed you cannot pick any. The way to do this is by to find 2 to the n minus t plus 1 basis functions of each ui and show all the m times 2 to the n minus t plus 1 of them are linearly independent. Because every space is spanned, the dimension is this guy. And the way to do it is to just try to find this number of functions in each of the space, and therefore we will get m times this number of functions in total. We want to show they are linearly independent by evaluation on certain points. Actually, the way we wrote in the paper is we directly try to find all these functions. We gave the definition of these functions, but I personally think this way is more natural to think about. Because why should we think of functions in the beginning? Any questions so far? Yeah, so now I just want to tell you what function we choose and why we kind of try to explain why these functions make sense by comparing the functions to the event over there. I will not show the details why they are linearly independent because then you just need to evaluate them on the correct points, which is kind of not hard to find them. Yes, so the way to do it for each I that is in M, for each subset I subset of the same part, because so how could we find that 2 to the n minus t, this number? We can just look at all the subsets of this guy. This will give us exactly 2 to the n minus t plus 1. So for each subset of the same part, this has size n minus t plus 1. We define Fii to be a multiplication of 3 parts. So in the part where Ai and Bi are distinct, we take xk minus Bik. In the part where k is inside I is a subset of Si, where they're the same, we take xk minus Aik. Actually, this you take Bik or Aik, they're the same. I don't know why I wrote this, but yeah. And in the part where they are the same, but not in I, you take xk minus 1 minus Aik. So this might look weird to you because I took this xk minus 1 minus Aik. actually in our paper we didn't write this way. I think they're like you will never use this in the proof, but this is just to compare to the method there, because since it's binary, it's either AIK or 1 minus AIK. And indeed, like here, this is the common part we always take in the family, like this part. The only freedom is on the other side of is on SI. And in SI, we just want to enumerate a subset and take this part. We don't care what you take there. And they are just a different basis of the same family. So it's okay to take this basis instead of that one, although this looks longer. Yeah. So this is a family. This is the functions we take, and I want to explain a bit. So why does this function maybe a bit make sense? So the way I think of it is the following. So let's think of the binary case. Or let's say alpha is any string in 0, 1 to the power n. And now, what does it mean by FII? And also, of course, AI and BI are also in 0, 1. Actually, it doesn't matter if, yeah. So what does it mean by FII alpha is not 0? Because usually in the proof of, in the algebraic proof, you want to evaluate the functions on some points to say, these guys are 0, these guys are non-zero, you get the rank out of the evaluation matrix. And so what does it mean by non-zero? So this means that alpha k is not equal to BIK for all k that is in BI. Right? Because so alpha k inside DI, they cannot be the same. And also alpha k is not equal to AIK for all k that is in I. Alpha k is not equal to 1 minus AIK for any k that is in SI minus I. So that's just conditions I wrote out of there. And in particular, since all the 3 strings here are binary, we can translate this information into that. So this is equivalent to say that alpha k is the same as AIK, because we know that in this DI, which means AI and BI are distinct, if it's not BIK, it must be AIK. And here in this part, alpha k is equal to 1 minus AIK. Because if it's not AIK and both of them are in 0, 1, it must be the other one. And the last guy, it is not the same as 1 minus AIK, so it must be AIK. Right? So this is the condition we get out of the 3 things, given that they are binary. So in particular, this already shows kind of it's similar to that case, because what it does is to enumerate over all the candidate alpha that will make EI happen. So when does EI happen? Alpha must coincide with AI on everything on DI, which is the condition here. The first one. And on the second and the third one, it is to enumerate which bits alpha is the same as AI, which bits alpha is different from AI. So this means that FII alpha is not equal to 0 for some I that is a subset of S is equivalent to that EI happens, given that alpha, AI, BI are binary. So this is the way I want to. Yeah, I'm not saying this in this way. It's no more. It explains why you can prove they are linearly independent, but at least it shows why this proof kind of makes a bit sense. And yeah, and for the actual proof of this, you just need to for each FII, you define some point to evaluate and show that you can order the functions and the points to show this matrix is upper triangular. And this requires some work. And this is basically the proof part. And I think in terms of your question, we can also show something like, we can also show when this is t plus s, and this is at most t, instead of 2 to the t plus 1, we show the answer of Hamming bound. If anyone is familiar, I don't have time to talk about it. The Hamming bound for binary error correcting code. We show the upper bound is this. And when s is equal to 1, the answer is 2 to the t plus 1. When s is equal to 2, the answer is still 2 to the t plus 1. Something like this. And it is tight when s is equal to 1, 2, 3, 4. Because of the, like, you can reduce, like for every error correcting code, you can construct AIs and BIs with specific n. And the tightness of error correcting code can show that this bound is also tight whenever error correcting code is tight by Hamming bound. And also when s, I think, is 7, t is 15, something like this. Yes. And so this is also kind of the more general version of Hamming bound. That's why I said it's a related problem. This is the only related problem. Yeah. So that's everything I want to talk about our paper. Thank you for your attention.
Is there any questions?
If we improve that kind of the Helly number, then does it imply the improvement of the error correcting code, the Hamming bound? We mean in this case, if we get the improvement on the Hamming bound, then it directly we can improve the Helly number.
I'm not sure.
Conversely, the conversely is also true. So,
I don't know actually. Because we only use this to prove the Hamming bound. I don't know. And also the other thing is we don't know any example where this setting, a general setting compared to error correcting code, the answer is larger than error correcting code. Like, can you construct one example with given s and t, whatever n it is, that the answer of this question, the largest m, is larger than the error correcting code, largest size of error correcting code? Yes.
If your alphabet has like 6 points, like do you do the probabilistic proof or the algebraic proof, or?
It depends on what bound you get. For the probabilistic proof, you can always get a 4 to the power t bound, whatever alphabet you get. That's because if you do this proof, you want to so here the crucial property is that alpha in every bit, alpha is either AI or BI. Like if AI and BI are different, it's either AI or BI. But if you have alpha bit bigger, then you have several choices. Like it's either, it can be alpha AI, it can be BI, it can also be different from all of them. Like, so basically, I think you have kind of 4 choices, something like this. And when alphabet is 3, there are only 3 choices by accident. And then you get 3 to the power t plus 1. Yeah.
Did you also consider about the skewed version?
Ah, right. That's yeah. Sorry, I should have mentioned. Yeah, that's the open question we mentioned in the paper. The problem here is that I didn't mention precisely how the functions, how we proved they are linearly independent. But indeed, we showed something like Fii, you will find a corresponding this. This is point, evaluation point. This is always non-zero. But Fii, if you plug in another point, this is 0 if something like I is bigger than j. So you compare, usually in the algebraic proof, you compare by the original indices. But here you compare by something else. And by comparing this, you already use the property like upper triangular. So our proof doesn't work at all for the skewed version. But It can be. We wrote a program for that actually. And the program cannot work when the length is larger than 5 or 6.
So this theorem is for arbitrary x, yes?
Yes.
And so the proof when x was r, this implies arbitrary x? I don't understand.
I think this implies arbitrary x because
Because it's in this particular metric or something like that.
yeah, because whatever, for example, you can always assume m is finite, and then given they are finite, you can always take x to be the set of all the entries that occur here. They're isomorphic to a subset of R because you don't care of anything except that they're equal or distinct.
Is it okay when the alphabet set is bigger than R?
So at least here, there's no problem at all, because you never use structure of the set. You can always say you pick a finite family of AIs and BIs, and then you take X to be the set of all the entries that occurred there, and you can assume these entries are subsets of R. And there, I think we tried before, we didn't write, but with some work, the Helly number thing, you can just do it because of this simple case. You can always try to reduce the, it will work.
Did you think about the colorful version?
Colorful version, no, not really. We did a fractional Helly thing and the PQ theorem. We did it. Yeah, because we are not very. I think we don't have. So for us, the motivation is more like from the proof side instead of the geometry side. If you have any suggestions, very nice.
Any question? So if no, thanks, speaker again.